G'day everybody. In this video, we're going to be focusing on the concept of impulse, building on what we already know about momentum. So we're continuing to look at inquiry question 3. We're looking at the motion of objects in simple systems and how that motion can be influenced by the interaction of objects, in other words, collisions. We're still building up to that concept of collisions today, but we're going to be looking at dot points 2.3, 0.3, and 4. The first one looking at this idea of graphs, of force being a function of time. That might look a little bit confusing at the moment, but it is related to this equation down the bottom here, which does involve force and time. I'm going to be looking at this dot point towards the end of this video, and once we understand impulse, that dot point is probably going to make a lot more sense. But what we want to start looking at is this equation here, which is all about impulse and looking at how it can impact collisions and interactions, because impulse has a huge impact on all of that. So today, our main aim is to first off define impulse and have a look at what that actually is. Then show how impulse is connected to momentum and Newton's second law. Apply impulse formula to a real world scenario. And then at the very end, we will start to unpack how momentum and impulse can actually have an influence on force in a collision. So here the impulse formula is this second formula that was related to momentum. It's delta P is equal to F net times delta T. So here it's really important to identify that impulse is the change in momentum. That is the definition. So you will see these terms getting used quite interchangeably. And as a result, the units of measurement for impulse and for momentum are the same. You can either be writing it as Newton seconds or kilogram meters per second. Either way works. So interestingly, Newton's second law, the way that we look at it as F equals ma, was not the way that Newton first described it. He actually described it in terms of momentum. And so Newton originally said that the net external force equals the change in momentum of a system divided by the time over which it changes. We can actually use F equals ma in our understanding of acceleration to bring everything back to this idea of momentum and impulse. So there are two key equations that we need to bring F equals ma back to momentum. That is our second law formula itself, which is F net is equal to ma. And as well, we're going to need the acceleration formula being delta v on t, so the change in velocity over time, which we can also write as v minus u, so final minus initial velocity over t. So what I'm going to do is substitute v minus u on t directly into our F net equation. So that means that F net is going to be equal to m times v minus u on t. We can then put all of our terms on the numerator together and it will look something like this. That means we can expand in our brackets, giving us mv minus mu on t. And we should notice here that mv minus mu is what we said was change in momentum in the previous video. We said that delta P was going to be the final momentum minus the initial momentum, which could be written as mv minus mu. So what that means is here in our working, we can change mv minus mu over t to simply be delta P on t. And that is exactly what Newton says at the top, that the net external force F net is equal to the change in momentum, so mv minus mu, divided by the time over which it changes. And from there, what we can do is clean this up a little bit to make it match what we saw in our data sheet before. So take this Newton's law concepts and rearrange it a little bit for the change in momentum, which is delta P is equal to F net times T, which means by definition, impulse is I. You may see it written or represented as I, which is delta P, which is F net times T, which is simply the change in momentum, or mv minus mu. All representations which mean exactly the same thing. So just to consolidate our concept, let's have a look at this impulse practice question. It should look really familiar to last videos. It's the same question, except we've been told how long it took to make this uniform acceleration. So again, I'm just going to draw up a little bit of a data column. So the mass is equal to 12,000 kilos. U is 80 kilometers an hour, which is 22.2 meters per second. V is 107 kilometers an hour, which is 29.7 meters per second. And we've now been given this t value as extra, which is 10.25 seconds. And that information is going to allow us to move from this momentum measurement to a force measurement. So to be able to calculate for force, we need to use our impulse equation, which is the change in momentum, which is mv minus mu. Based on previous calculations, we found that to be 90,000 kilogram meters per second. However, what we can then do is rearrange for our impulse equation, which is in your data sheet. Delta P is F net times T. So if we want to rearrange for the force applied to the bus, that'll be delta P on T, or the impulse divided by T, which means we just need to substitute our two values in 90,000 divided by our time, which is 10.25. And that should give us this number here. And based on the number of significant figures provided in the question, we had a 12-ton bus. So that's two significant figures. Our answer should be in two significant figures as well. So 8.8 times 10 to the 3 newtons. In this second problem, what I want to show is that we can graph essentially, or represent impulse as a graph by showing what happens to force as a function of time, or as time progresses. So we know already that impulse is essentially force times time, which looks quite similar to a simple area formula, assuming that we had a quadrilateral. Essentially, when we have a graph, just like we've done previously, we can calculate for area underneath the graph. And if we do so, that can give us our desired value. In this case, it can give us impulse. So if we do a little bit of geometry on the graph, we can calculate the impulse, assuming that we have a time and a force axis being displayed. So in this scenario, the impulse, which is on the tennis ball, will be all of this area that is here. And to calculate for that, all we need to do is calculate the area of both triangles. In both scenarios, the force is 200 and the T1 and T2 values are 0.015 seconds. And when you put all of that into your calculator, you should get 3 Newton seconds, which again is our impulse. Finally, I just want to start to talk conceptually about momentum, impulse, and its role in collisions. And I want to think about what would happen in a scenario where you have an object that collides with another object, and it makes the object stop completely. Best scenario to sort of think about this would be in a car crash. So in a scenario where two objects collide, so it could be two moving objects, or it could be a car and a wall, or something like that. But let's think about collisions where VF is equal to 0 meters per second. So in these scenarios where VF is equal to 0 meters per second in a collision, we can assume that delta P is going to be constant. No matter what's happening in this scenario, as long as our initial velocity, our u, is the max velocity or the starting velocity, and v, which is our final velocity, is equal to 0, you're always going to have, again, that same change in velocity. In other words, impulse is always going to be the same, which is interesting when we start looking at the impulse formula. So impulse is equal to F times T. If we have a collision and impulse is always the same, what that means is if the deceleration happened in a really small amount of time, we go from u to v in a small amount of time, then that means there's going to be a lot of force applied to the object to get it to decelerate really, really, really quickly. However, if we have a lot of time for the object to decelerate, to go from u to v, then you're going to need a smaller amount of force being applied to get that deceleration happening. And you don't have to apply as much force because you are slowing the object down over a longer period of time. And that can be mathematically shown by subbing in various values into this ft expression, assuming again that your I value or your impulse is going to be constant. We will discuss these applications a little bit further in class though, but there's, I guess, the base numeracy component to help you there. Thank you very much, everyone. In the next video, we're going to look at the conservation of momentum as well as the conservation of kinetic energy and look at how that's being applied in collision scenarios, which really brings all of these big concepts that we've been looking at over the last couple of inquiry questions together as we start to analyze what happens to objects when they collide. But until then, have a good one.